Okay, so the next problem that we're going to work is going to be problem number 738. So we're going to skip over 34. We're going to go to 738. So what I'm going to do is I'm going to go underneath our camera first and kind of introduce the problem. And we are going to be looking at this motor on a car wash sprayer. It rotates counterclockwise at a constant rate of 120 RPMs. So what that means here is that we've got a W2 of 120 going counterclockwise, but our angular velocity, or I'm sorry, our angular acceleration alpha is 0, okay, on the crank. At this instant, theta is 40 degrees, so we have that here. Use the relative acceleration method to graphically determine the angular velocity and angular acceleration of the nozzle arm. So this nozzle arm right here is pivoting or rocking around, you know, its center of rotation here. So it's going to be rocking back and forth. So they want to know what is W4 and what is alpha 4. Okay, that's what we want to know about that. Okay, that's what we want to know. So I've kind of started a little process here, if you would, and looking at our problem. And I'll give you a chance to copy this down. So this is problem 738. What we know is that W2 is going at a constant rate, 120 RPM clockwise, and we need to find that W4 and alpha 4. Okay. So we've already, or if you haven't gotten to, you want to, number one, get your kinematic diagram all set. Okay. And once we have that all set, we're going to move into, we have to do our velocity work first. Okay. We need to determine what the velocity of point C is, which we're going to look back at our diagram and find that it's on the endpoint of link number 4, which we need to find the angular velocity for. It's going to be equal to vectorially vector number 2, or velocity of B, plus vectorially C relative to B. Okay. And kind of using our process that we have been, because we know everything about link number 2, the velocity of B is going to be the angular velocity of 2 times its radius of rotation. Okay. Then we're going to be moving into, once we get our relative velocity all set, we're going to be moving into relative acceleration. Now, this time, because point C is on a rotating link, or it's on a link that's pivoting about a fixed center, it's going to have a normal and a tangential component. Okay, a normal and a tangential component.
So lower.
Yep. So right here, this is pivoting around that. So it's not going in a linear fashion. So that's why it's going to have a tangential and a normal component. All right. Before, we only had just the acceleration when we had that slider, because it was only going in a straight line, right? And then equal to, we're going to expand out the acceleration of B to be normal and tangential there as well. And then the acceleration of C relative to B, normal and tangential there. Okay. Now, it's not a bad idea. I always like to kind of work backwards to understand why we're doing the steps that we are in the order we are. So the reason we need to do this work up here is because we're going to need the velocity of B, which we're going to get. We also need to know what that velocity of C relative to B is, so we can use it down here to do our calculations for our normal. And then we need the velocity of C, its value, to calculate the normal down here as well. Okay. So let's write out what each one of these magnitude-wise is going to be equal to. So as we look at the normal component of A, even though I'm not talking about numbers, I'm just talking about equations. So when we look at a normal component, we've got W squared, or angular velocity squared, times the radius, or we can use the velocity of the point on that link divided by the radius. Now for link C, or I'm sorry, for point C, I'll just point here rather than going back and forth. Point C is right here. All right. And because point C is on this link that is rotating, okay, we are going to be determining what the W2 is of that link, or I'm sorry, what the W4 is of that link. And we're going to use this equation. So we have to use the velocity here that we get from the velocity equation above. So to calculate the normal component, we're going to be taking the velocity of c squared and divided by that radius. And then once we have that value, well, you know what? Well, we'll see what order we do this in, but so we'll use that value. Then our tangential. Now, our tangential is actually going to be a magnitude that we're going to get from the vector diagram. It's going to be unknown to us, and we're going to use it to then calculate that alpha of number 4. Okay, so this one, we won't know the magnitude. We're actually going to measure it. Okay, measure magnitude, but its direction we know to be perpendicular to the normal. And this one we'll know both, because the normal always points from that point that we're looking at back towards its center of rotation. So C, we know where its center of rotation is. Now, as we cross over, the normal component of the acceleration of B is going to be using either one of these again, okay? And I'm just going to write the VB squared divided by R for its magnitude. Okay. And then its direction as well is going to be pointing from point B back towards its center of rotation, which is point A. Tangential. Tangential, as we look at this problem, this is another one where it says that we are rotating in counterclockwise at 120 RPM at a constant rate. So there isn't an angular acceleration on our crank. So that means we're not going to have a tangential value, okay? Because the tangential value, we would take that radius of rotation times its angular acceleration, and the angular acceleration is 0 because it's going at a constant rate, okay? So that one's going to be 0 because alpha is equal to 0. We'll say alpha 2. The normal of C relative to B, this is going to be the velocity of C relative to B squared divided by the distance of C to B. This one we get from our vector equation above. Okay, the magnitude of C relative to B comes from right there. Okay. And then this velocity comes from there, and then that comes from there. And then the tangential component. Okay, so this one we're going to know magnitude and we're going to know direction. So the tangential, this one we're going to, I mean, we could measure. I don't think we end up needing to measure it. So we won't know its magnitude, but its direction we do know to be perpendicular to C relative to B. Okay. So we end up having, this is not an unknown, this goes to 0, just like, so we end up having 2 unknowns and they are separated by the equal sign. So we're in good shape. Okay. All right. So using the kinematic diagram that we drew, let's now construct our vector equation for our velocity. But before we can, we've got to calculate our value for VB. Okay. So to do that, I need to convert my 120 RPMs into radians per second, right? So I'll do that work over here. So this will be W2 is equal to 120 revolutions per minute. And I want to convert that to 1 revolution is 2 pi radians. And 1 minute, 60 seconds. So W2, you guys get 12.566. Yeah. And then that's going to be the number that we're going to put in here. So this is going to be equal to 12.566 radians per second times its radius. So from this illustration, the length right there is 3 inches. 3 inches. Okay. So my VB magnitude, I have 37.7, right? 37.7. Yeah. And that's going to be inches per second. Okay, inches per second. All right. So now we're going to take this number. This is the magnitude of our velocity of B, and we're going to construct our relative velocity vector equation. So going over to AutoCAD. So from our vector diagram here, link number 2 is right here. So I'm going to use that link. I'm going to change this to vector, and I'm going to draw a line perpendicular to it, right? Velocities, I think are, I don't know, they're kind of easy. Directions are always perpendicular to something, right? Perpendicular to something. So this is the velocity of B. Now I need it to be 37.7 inches per second. So I forget what these lengths are. So if I do 37.7, is that like, ooh, that's really big. That's really big. So I think I'm going to do 3.7. How about that? 3.7 sound good? Okay. And then we just have to remember 3.77. We just have to remember to do the multiplication. Extend. There we go. Get rid of this. Put my arrowhead on. And then this is going to be my velocity of B. So that's the direction of that one. Then I need the direction of C relative to B. So that's going to be a line perpendicular to the line connecting C and B. So link number 3, right? Link number 3. Perpendicular to link number 3. Oh, did I go the wrong way? Counterclockwise, you are correct. Thank you. So I just need to mirror this. I apologize. Thank you for checking that. And I'm going to be along that line. Get rid of that. Thank you. There we go. And I'll put it on the end point so it's not in the way here. Yes, counterclockwise is the way that this is going. I think the last one we did was clockwise. Okay. And then this one is going to be the velocity of C relative to B. Right. And we don't know arrowhead or direction here. This is just line of action. And then our last one is going to be the velocity of C. So velocity of C is going to be perpendicular to the link that it is rotating around that fixed center on. So this is going to be a line, and it's going to be perpendicular to link number 4. So I'll move this here to that end, and then we'll call this, again, we don't know the exact length of it yet. We'll get that from our vector diagram. That's going to be V. There we go. So as far as direction wise, we get our directions for those velocities from our kinematic diagram. Once we have those in place, we are then going to establish our origin. Okay. And then we're going to do our vector equation. Move this. Oops. Move it over here. So I'm going to copy my velocity of B, put it at the origin. I'm going to copy the line of action of C relative to B. I really don't know which way this is going, but I'm just going to put it on the endpoint here. Let me move my VB there. And then I'm going to copy my velocity of C, start back at that origin. Oh my goodness, look at that. And you're going to get this to go there. So those are right next to each other. Did yours do the same thing? Yeah, yeah. So let me trim away what I don't need. That one's teeny, teeny, tiny. It's cute. It's a cute little vector, don't you think? And I'm gonna this maybe like here-ish. A little smaller. Let's see. There we go. Make sure to always add your arrowheads. That way that confirms the direction. Okay, so then I've got to move this one on this side. And this one goes over here. And then this one goes there. All right. So now I'm going to add my dimensions. So a line dimension from here to here. That's going to be my C. And then I need my aligned dimension for C relative to B. And then I might as well add the one for velocity of B, which was what we used. Okay. So as we look at the numbers, just to want to get a confirmation if anybody is this far on the magnitudes of your vectors. You got it? Okay. All right. I'm going to scooch this one over. And I'll give everybody a chance to catch up. So I'm gonna stop the recording for a little bit. I'm gonna pause it and then we'll be back. Okay. So once the vector diagram is done, these are our numbers. Now, as you recall, we scaled these. So we moved the decimal place one place to the right to get our values. So for the velocity of B, it was 37.7. So that means that our velocity of C relative to B is going to be 3.4 inches per second. And then our velocity of C is going to be 35.323. So you want to write down those numbers because they're going to come in handy for our. Oh, no problem, David. That's totally fine. So that we're going to be needing those for our velocity or for our velocity values in the acceleration equations. So going back over here, we know that our velocity of C was equal to, now I've got to go back and forth. I'm going to write them down. The velocity of C was equal to 35.323 inches per second. Our velocity of C relative to B was 3.428 inches per second. And our velocity of B, we know, was 37.7 inches per second. Okay, 37.7 inches per second. Okay, so I wrote those values down over here. Now, the problem asked us for the angular velocity of that nozzle arm, which is our W4. We can calculate W4 now. Okay, so why don't we go ahead and do that? So W4 is here, and we know that our point C was at that location, and we know what the velocity of C is. Okay, so to calculate W, right, we can just rearrange this equation. Our W, or our angular velocity, is going to be equal to the straight line velocity divided by the radius, right? So our straight line velocity here would be VC, and the radius is going to be the length of that link. So we would say that W4 is going to be equal to VC divided by radius C. So we know VC to be 35.323 inches per second divided by the length of that link, which was 6 inches. Inches cancel out here. Our W4 Yep, I get that same thing. 5.887. And what are our units? Whoopsie. Radians per second. Exactly. Radians per second. Okay. Which means we need to convert this to revolutions per minute, right? So 2 pi radians, 1 revolution on top, 60 seconds on top, 1 minute on the bottom. Oopsie. Okay. Minutes don't cancel. Oh, where's the eraser? Seconds cancel, radians cancel. So we're in revolutions per minute. So our W4 officially Yep, 56.2. And that would be RPMs, right? And then additionally, what's the direction it's going in? What's the direction it's going in? So we want to say if it's going clockwise or counterclockwise. Counterclockwise. So if we look back at our vector diagram, this is going down and to the left, right? So if this is, oopsie, if this is going down and to the left, you're right. It's going to be going counterclockwise. Correct. All right. Let me go back here. So this is going to be counterclockwise. And then that's going to be our first answer for this problem. Okay. Any questions at all? These are kind of, okay, I'm not going to say they're fun, but they're enjoyable, I think. Exactly. It's not too bad now, right? We've done enough of them, especially the velocity part, Okay. So now let's use these numbers and focus on the acceleration part. Okay. So, I'm going to start on, well, it really doesn't matter. We'll just move left to right. So the first one we need to determine the magnitude for is going to be your normal component of C with the equation we see here. And then we're going to do the normal of B, the normal of C. And I think that's it. We're just going to do the normals. Okay. So I am going to grab an extra new piece of paper here. And we will calculate each one of these. So I don't know, I'll call this probably step number 4. Step number 4. So the acceleration normal at I'm sorry, C. C. It's going to be equal to the velocity of C squared divided by the radius of C squared. Now, honestly, whether you use this equation or you use the W equation, it doesn't really matter, but the velocity of C is the least calculated value, if you would, right? Right, yeah. So this number is equal to, so it's 35.323. Oopsie. And that's inches per second, and we have to square that entire value. And then we're going to be dividing by 6 inches. Okay. So the acceleration normal at C is going to be 207.95. Is that what you guys got? Inches per second squared, right? Okay. Then our next one is going to be the normal of B. And that one's going to be VB squared divided by its radius. Okay. So acceleration normal B going to be the velocity of B squared divided by the radius to B. So we know that number to be 37.7 inches per second. Square that entire value divided by its radius was 3. Three inches. So our A normal B. Or 73.76. Yeah. All right. And then our normal of C relative to B. Okay. So C relative to B, we measured that from our vector diagram, 3.428 inches per second squared, divided by the distance between B and C. The distance between B and C is 10 inches, right? That's going to be the length of link number 3. So our A normal C relative to B. Maybe not 3.428. Yes, it is. Did you get 1.175? Yeah. I mean, the answer makes sense to me, but it seems really, really small, but it is a small little vector. Okay. All right. So now we're ready to generate this vector diagram. Okay. Let's review the directions. So now we've got these magnitudes of those 3. Okay. If we go back over here and we use our equation sheet, the first one here is that normal. Okay. It's the normal acceleration at C. So our normal acceleration, the direction is always going to point towards its center of rotation. So as we look here at this, velocity of C is, or I'm sorry, point C is right here. It's going to point towards the center of rotation, that normal, and its center of rotation is right there. So its tail is going to be at C, and it's going to point towards point D. Okay. Now the tangential is going to be perpendicular to that radius or perpendicular back to the normal. And it's either going to go in the direction of rotation if it's accelerating, or it's going to go opposite if it's decelerating. Okay. We really don't know. We really don't know at this point what it's doing, because when we do our vector diagram, we'll know its line of action is perpendicular, but we don't know which way the arrow is going to go yet. All right. And that'll be decided in the vector equation, vector diagram. Okay. Then as we move over across, we know both magnitude and direction of that normal at B. So B is this point right here. Its tail is going to be at B, and it's going to point towards A. All right, right down that radius of rotation. The tangential at B, it's going to be 0, but it's 0 because this is going at a constant rate, but it would be tangent or perpendicular if it was going to be there. Okay. Normal at C relative to B. Normal at C relative to B, we have our magnitude. Its direction is going to go from point C and point towards point B. All right, from point C. So the tail is at C and the tip is pointing towards pointing towards B. And then the tangential, we don't know its magnitude, but it'll be perpendicular to link number 3. Okay, so knowing all that information, all right, let's generate this acceleration vector diagram. So we're going to go back to AutoCAD. Now the numbers we're dealing with are 200, 401. 200, 401. So it probably makes sense. I guess I'll just do divide by 10. So it'll be 2.07, 4.7, and then 0.01, which is really little. Okay, that's all right. So we will first start with our origin. We will deal with it. And I'm just going to start randomly, like here-ish. And I might have to move if I need to. Okay, so now we're going to start with the side that we know the most, which is this, which is going to be the normal acceleration of point B. Okay, so we know that the magnitude of it is, it's going to be 4.73, and it is going to be along a line that's going to be in the same direction as link number 2. So I am going to copy link number 2 here. We're going to start the tail of that vector at the origin. Okay. And I'm going to change this to a vector layer. Okay. Right. And I need B to be, let's see, I need B to be 2.0795. Trim. And then I'll draw my lines. Okay. So that's the acceleration of V of, oopsie. I used, oh, I did do the wrong one. Thank you. I did the velocity of C. This needs to be 4.73, right? Gosh, I was doing so good all night. What happened? Here we go. Thank you, Adam, for catching that. Okay. Okay, so this is going to be the acceleration normal at B. Here we go. Okay. So 4.7376. All right, now on the endpoint of that normal component would have been the tangential, but that's 0. But we're going to add the normal of C relative to B. Remember, the direction is going to go from C towards B. So on the endpoint, we're going to grab link number 3 is the same line of action as that normal. I'm going to put it on my vector. Okay. And then this distance from here is going to be, oh, this is that teeny one, isn't it? Oh my goodness. It is divided by 10.01. Is that right? 175. Yeah. Oh, it's the littlest. It's the littlest. It's like, what is that even, right? All right. Whatever. I'm not going to worry about this right now. not right now. We will worry about it, but I'll put the arrowheads on in a little bit. All right. Our next one then is going to be the tangential. The tangential is perpendicular to that, right? So that is going to be the same line of action as the velocity of C relative to B. So I'm just going to grab this line because it's perpendicular to, and on the endpoint right here is where that one's going. Okay. So I'll add my little arrowheads, I guess, as long as I'm in here. Little arrowhead. Line, little arrowhead. Okay. So now what we've done is we have all of the vectors in place, line of action wise, that we know. So we have magnitude and direction of A normal to B. We have magnitude and direction of A normal C relative to B. And now we have line of action of the tangential, right? So let's go back and look, and making sure that you've got that teeny tiny little one in there, because that does set the direction of the tangential. Okay. Any questions at the moment? All right. Now we're ready to jump to the other side. Okay. So I'm going to jump to the other side. I'm going to switch to my green. And we're going to start with what we know. we know the magnitude and direction of the normal acceleration of point C, okay? Its magnitude is going to be the 207.95 or 2.0795, right, is what we're going to draw it to. And it is going to point from point C to its center of rotation, okay? So that means it's going to be along link number 4. So I'm going to do a copy of link number 4. And I'm going to start its tail. Oh my gosh, is that right? From, yeah, it goes from there to there. Okay. Okay. And this is going to be rain. Okay. And we know that its line of action, right? Or we know its magnitude is, so I got to do a radius, 2.0795. And I'll label this one. I didn't label my last ones. I should have. All right. And then okay, now on the endpoint of that, we're going to add the tangential of C. Now the tangential of C is just going to be perpendicular to the normal, but we don't know its magnitude. So on the endpoint of C, we're going to draw a line perpendicular to link number 4, which we already have a line of action from the velocity at C. So we're going to go like that. And we are going to go on the very end point of C. We move this. All right, and look at that. We have an intersection. If you did them the same length as me, which you may not have. Okay. So let me grab and I'll put my labels on for what the other items are here and down there. So this one is going to be tangential. This is the tangential of C relative to B. And this was the normal of C relative to B. Okay, that's the teeny tiny. So now I'm going to trim these, okay? And based on the adding on my endpoint of my tangential, my line is going to go from here to here, from here to here. And then the endpoint of my tangential of my C relative to B is going to be here and here. Whew. What do you guys think? Now, we're trying to find the angular acceleration of link number 4, So if we look back at our equation sheet, my angular acceleration is right there. So what I need is that tangential component, right? So I need to measure the tangential component in order to be able to calculate my angular acceleration of that link, right? So step number 5, angular acceleration of link number 4 is going to be equal to, I'm going to rearrange this equation. Okay, so to get it by itself, I'm going to divide both sides by the radius. So it's going to be the tangential acceleration of point C, because point C is on link number 4, and it's going to be the radius to point C. Okay, so that means I have to go back to AutoCAD and measure the length of the tangential acceleration at C vector. So I'm going to grab this one and this one, and that is its length. I'm going to change this to note. Okay. So my number, I need to multiply that by 10, is going to be 26.753 inches per second squared. And I'll zoom back out here. And I'm going to divide that by 6 inches, which is this length right here, 6 inches. Okay. So angular acceleration of link number 4 is 4.456. Radians, right? Radians. Inches are canceling here. So inches cancel inches. So it's nothing per second squared. Radians per second squared. And the good thing about it is that it is, those are the units that we express angular acceleration in. So we don't have to do any, going back to revolutions or anything. So did everybody get this number? We're not quite done with it. We have to do a little bit more, but did everybody get that number? 4.456 radians per second squared. And I'm going to go back over here just to be sure. And then this is our vector equation for the acceleration. Same numbers. 2 point what? 2.686. Oh, we'll call that good. You got 2.68?
I got 2.686.
Oh, okay. I think I got mine on the right endpoints here. Maybe it was in the rounding of one of the numbers, but yeah, that's way close enough. Way close enough. Okay. Now, as we look back at our work, so we've got our numbers. So you got 4.456 then? Or ish?
Sure.
Very close to that, yeah, or very close. Radians per second squared. Now, the only thing we need to add is if this, or the direction that this is going, is it going clockwise or counterclockwise? All right. So we need to look back at our vector diagram. So you'll notice that the tangential is going down and to the left. Okay. And when we look over here, if we're going down and to the left, the angular velocity is also going to go in a counterclockwise direction. So is this accelerating or is this decelerating? It's accelerating, because notice that the velocity is going in the same direction, right? The velocity C is going down and to the left, so the angular velocity is going to go in that direction. The tangential component of the acceleration is going down and to the left. So is the angular acceleration. So because they're going in the same direction, it's going to be accelerating. Okay, good. Oops, wrong one. Okay. So this is going to go in what did I say? Counterclockwise, and then accelerating, not decelerating. There we go. Virtually, does anybody have any questions as you're looking at what we've been doing? Okay, I'm not seeing anything. No news is good news to me, so that's okay if you're not responding, no problem. And then I'll go back to the AutoCAD work to make sure that this all kind of makes sense to us. So I'll move these together. Put this one up here. And then I'll my little, yeah, it's kind of hard to see it all at once, but I'll try to go there. Okay. Any questions at all on the process here? So this one involved a little bit of extra work because of the oscillating link, calculating those rotational velocities or angular velocities and angular accelerations. Okay, just really kind of one extra step in calculating on each one. But otherwise, as we look at the process, it was really very similar. And then also just making sure that we remember the equations we need to use, as well as the directions that each one of these vectors go in. Okay. So if there aren't any questions, we'll stop the recording, and that's problem number 738.